In this Lisp for Beginners course, you'll discover why this elegant programming language has influenced computer science for over 60 years. Lisp's elegant approach to handling code as data, combined with its powerful macro system and functional programming paradigms, offers developers unique insights into program architecture that remain relevant and influential across modern languages like Python, JavaScript, and Rust. Alberto Lerda teaches this course. He is a DevOps engineer who loves Lisp.
If you have ever heard people talking about Lisp, it was probably related to how powerful its macros are. My goal is to spend a few videos talking about them. No previous experience with Lisp is required, but knowing another language may be useful. Before we can start writing macros, we need to understand how to run a Lisp program and an introduction to the language. There are many flavors of Lisp. For this series, we will use Common Lisp, in particular the SBCL implementation. First of all, we need Lisp installed. If you are on Linux, you can install SBCL using the package manager. For example, I am on Fedora, so I can run sudo dnf install SBCL. If you are on Ubuntu, you can use apt. The same is true for macOS. You can install SBCL using brew. We can verify that the installation was successful by running sbcl. This command should show us the Lisp interpreter. You may notice that if you write something, for example 42, and then I try to go back using the arrow, some weird character appears. My suggestion is to install the rlwrap command. So delete what I delete what I have written. I run quit to exit the interpreter, then I can install rlwrap. From now on, I can run the interpreter using rlwrap and then sbcl. This time, you can see that I can move with the arrows. Now let's see how to install SBCL on Windows. If you are on Windows, you can download the installer from the official site. Going on the right, download, and choosing the right architecture. Once it is downloaded, you have just to run the installer and follow the setup. As with Linux and Mac, we can verify that the installation was successful by running sbcl on the command line. To start writing our Lisp program, we also need an editor. For Lisp, there are quite powerful development environments like Emacs, but to get started, they are not necessary. For the moment, we just need a text editor. Any is fine. A common choice nowadays is using Visual Studio Code. Let's start it in the current directory. You may want to install the Common LISP extension. Such that when we create a new file, the main advantage of the extension is that it colors the parentheses. That we will see is a really useful feature. For the moment, just write the instruction to print something on the screen. We will come back later on what this means. And save it. let's open a new terminal. And when we want to run a Lisp program, we can write sbcl ---- script and then the name of the script. Other times we don't want to run directly a script, but we want to run some command interactively. In this case, we can just run sbcl, and as you can see, a Lisp interpreter gets opened. Now I just want to show you what happens when you write something wrong on the command line and how to return to the usual Lisp shell. For example, I write this command, which does not exist, and I press enter. As you can see, the shell has changed. In particular, we can see which is the error. The variable is unbound. I have written the name of a variable that I've never declared. For the moment, we can just press abort until we return to a star, which means that we are again on the usual Lisp shell in which we can enter expression. For the moment, we have finished. Next time, we will explore the shell more in detail. This is the second video in a series on Common Lisp. If you haven't seen the first, you may want to look at it in order to have a Lisp interpreter installed on your PC. Today, we will explore more in detail the syntax of Lisp. Let's open a Lisp interpreter. On Windows, just run sbcl in the terminal. On Linux, you may want to run it inside RL-RAP. In Lisp, everything is an expression, or better, a symbolic expression. So, learning to write a Lisp program is a two-step process. You have to understand how to write expressions and how they get evaluated. Every time we type something, the Lisp interpreter first reads it, then create a Lisp object that represents what we have written. It evaluates the object, then it chooses an output representation, and finally it prints it on the screen. This is known as REPL, read eval print loop. As you may imagine, in Lisp we have numbers, and for example 1, 2, 3, and they get evaluated to their value. We have integer and floats. Then there are the strings. Again, they get evaluated to themselves. Symbols have to be bound to some values. For example, pi get evaluated to 3.14 and so on. Now let's discuss a more interesting object, the list. A list starts with a parenthesis, then there are some expressions separated by a space, and then there is another parenthesis. When they are evaluated, they are basically functions. The first element is the name of the function, while the others are the parameters. At first, these may seem strange. In other languages, we have operators, like plus, that are in the middle of the arguments. And we have functions whose name is written before the parentheses. Lisp doesn't make exceptions. Treat all of them the same way. Despite looking strange at the beginning, this is one of the features that gives Lisp its power. There is no difference between the built-in functions and what the programmer comes up with. With your current knowledge, you could use the Lisp interpreter as a powerful calculator. to get used to the syntax, let's try to write one solution of the equation x squared plus 6x plus 8. First of all, we have the ratio of two elements. In the numerator, we have the sum of minus 6. In this case, there is no space between 6 and minus, so this is treated as a negative number. Plus the square root of the difference between two products. In the first one, we have 6 squared. And then we have the product of 4, 1, and 8. In the denominator, we have the product of 2 and 1. And we can see that this is the solution of the equation that we started with. We can verify this. In fact, in the equation, we have the sum of 3 elements. The first one is minus 2 squared. Then we have the product of 6 and minus 2. And finally, 8. And the value is 0. Lists can also be used as data object. We have to make it prevent evaluation. For this goal, we have to quote it using the single quote mark. Let's make an example. We have already seen what happens if we write plus 1 and 2. This is the sum of two numbers, 1 and 2. But if we put a single quote mark in front of it, the result is the list itself. Lists are not the only object that can be quoted. We can also quote symbols. For example, pi returns a value, while if we write quote mark pi, this returns the symbol pi. That's it for today. The next time we will write our own Lisp program and we will see why the objects we have defined today are useful. This is the third video in a series on Common Lisp. I have a file, example.lisp, and the terminal open in the same directory as the file. Today we start writing more interesting programs, using local variables and conditions. Now we want to write a function that lets the user insert its name, and then it prints the name on the screen and returns the name itself. Let's start by writing a function that asks the user for its name and returns it. We define a function, ask the user for its name. Now there is a small technical details that we have to flash the output. And finally, we can read the name. Now we want to use this function to read the name once and then print it and return. We need a local variable which can be introduced using the let command. Define another function. As usual, let is a list. Its first element are the binding that we want to introduce, which is a list whose elements are a list with the name and value. Name, ask name. All the remaining expression in the let list can use the variable just defined. For example, format p, in which we print a is a place mark which tells the format to read the next parameter in the function call, which is name. The way it works is similar to function definitions. When a let list is evaluated, its value is the last expression in the list. In this case, name. Let returns the value of name, and then the function returns the value returned by let, which is the name itself. This may seem difficult, but when you start using it, everything becomes much more clear. Let's try to run it. Print is another function to print on screen. And we can run from the terminal using sbcl, script, and then the name. He asks for us name, and then the first output is the one from format, while the second is the one from the return value. Inside the let, we can have even more than one definition. For example, we introduce the name variable and the variable another, in which we use again as name. And then we print both of them to screen. Let's try to run it again. What if we want to change the value of a variable after it has been defined? We can use the setf form. Let's remove the second variable. And now we want to change the value of name to a greeting. Setf name, and then we want to concatenate strings, which is the string hi, with the name, with the exclamation mark. And then we print directly this string and return it. We can see that the value of name has changed to the concatenation of those three strings. You may encounter a strange error if you try to reuse a variable inside a definition. For example, let's delete what we have written, and then we just introduce a variable x, whose value is 42, and then another variable y, whose value is x. And let's try to print everything on screen. Terpre just print a new line. Variable x is unbound. The problem is that let works in parallel, and so you cannot reuse the variable inside the definition. The solution is to use let star instead. Now, the next step in writing a more useful program is writing some conditions. For example, we want to decide whether a number is positive, negative, or 0 and print it to screen. We can write a condition using if. Let's define a function print sign, which takes as input a number and checks its sign. As usual, if is a list, and it expects three expressions. The first one is the condition. We ask if n is less than 0. Then what to do if the condition holds, and what to do otherwise. In this case, we want just to print negative, otherwise we print positive or 0. The last expression is not mandatory. Let's try to run it. This way of writing the program is not the optimal one. We have already seen that every list, when evaluated, returns something. In the case of a if, the return value is the value of the chosen branch. What this means is that we could write the same format as this way. The return value of the if is either the string negative new line or positive or 0 new line, and so we can format it directly. We can see that the return value is the same. We could even introduce a new format string and then return just the string negative or positive or 0. Finally, we can also decide whether it is 0 or positive using another if. When we have multiple branches, there is a syntactic sugar that makes the code more readable, which is the cond form. Instead of using if, we can use cond, which takes multiple conditions and what to do in each case. For example, we have n less than 0, return negative, equal to 0, return 0. In all other cases, this is always evaluated to true, return positive. And we can see that the return value is always the same. Inside the list which tells what to do in a command, we can also have multiple statements. For example, first we start to format something, choose a branch, and as usual the last value is what will be returned. We will see that the if and cons are strictly related to one another. Let's return to if and write a function that takes a number, and if it is even, it just divides by 2, otherwise it multiplies by 3 and add 1. So let's delete what we have done. And then we define a function, next number, which takes as input one number. It checks if it is even, and in this case it just divides by 2. Otherwise it multiplies by 3 and sum 1. Let's try it, and it returns 3. If is different from the fun, let, or con. We cannot have multiple statements inside a branch. Suppose that before dividing by 2, we want to print something on the screen. In this case, we cannot just write a format like this. Because if does not know how to group the branch in which it holds and the branch in which the condition does not hold. We have to be explicit using the program form, which runs multiple statements and returns the value of the last one. In this case, we want to group the format and the division, so we write program, and we put inside those two expressions, and we can verify that it first print the string and then the value. In this video, we have seen how to work with variables and how to make branching in Lisp with two different syntax. The next step will be making some loops. Hi, this is the fourth video in a series on Common Lisp. We are looking at how to write imperative code in Lisp. We have already talked about variable and branching. Moreover, in the meantime, we have shown how to deal with input in Common Lisp. The next step is writing some loops. The main loops type in Lisp are loop, do, dotime, and doList. Loop deserves a video for its own. We will talk about doList after looking at list. It remains dotimes and do. Let's start with the easiest one, dotimes. With dotimes, we can repeat an operation an exact number of times. This is commonly implemented in other languages using for loops. Let's write a program that reads n numbers and sum all of them. First of all, we need a function to read a number from the screen. We define the function readNumber. the first line write a string on the screen, then we ensure that the string is really shown, and finally we read a string and convert it to an integer. Then we start a function that actually asks the number and sum them. It takes as parameter how many numbers we want to sum, and we need to set a variable to 0. This variable will contain the total that we have summed. We have already seen let. It lets us introduce local variables. Now we need to repeat a fixed number of times the read number function. We can use dotimes. It takes as parameters a list in which there is a variable name and a limit which specify how many times we want to repeat the body of this loop. In our case, n. The counter will go from 0 to n minus 1, which means looping exactly n times. In particular, we will have to assign to total the sum of total with read number. Finally, we can try to output the result. Let's try it. Oh, a typo. Let's try it again. We forgot to return the value. Immediately after the dotimes, we have to return the total. And we can see that now it works. We know that in Lisp, every expression returns a value. Let's look at the value returned by dotimes. We can print it. It returned nil, but we can control it. Next to the variable name and the limit, we can set the return value of the loop. For example, we want it to return total. So I can remove the print C and the value that I returned immediately after the loop. This way, the value returned by the function is exactly what dotimes returns. And we can see that it still works. In this case, the two approach, using total directly as a return value or putting it as return value of dotimes, is the same. It may be useful if the results depend on the I, and we wouldn't have access to it outside the loop. And that's basically it for dotimes. useful for a specific task, but if you need a more complex loop, you have to look somewhere else. For example, at do, which is the most complete form of looping inside Lisp, but also the most complex. Let's try to rewrite the same program using do. So instead of dotimes, we use do. First of all, do takes a list of variable declaration and how to increment them at each step. So we just want to declare the variable I, which is 0 at the beginning, and it can be incremented using the plus. Then we have to specify the condition that makes us exit. In this case, when we reach n. Next to the condition, we can tell Lisp the return value, just as we did with dotimes. Pay attention to the nested list. We could have multiple declarations, and in the return value, the condition is the first element in a list. Let's run this version of the example. And we can see that we obtain the same result. And that's it. We have rewritten a dotime using only a do. One may wonder why dotimes exist if it can be written so simply using a more complete form of looping. The reason is that when you use dotimes, you are helping who will read the code after you, being more clear on what you want to do. Now let's change the exercise. We want to sum numbers as long as the user doesn't write the number 0. So we don't know at the beginning how many times we will have to loop. Thus we can't use dotime. But we have a more specific condition, which is an input that the user will supply. This time we could use the I as the number received by the user. And so we sum directly I. And we initialize I using read number. But read number is also the way to read the next value for I. Finally, we will end the loop as soon as I is the value provided by the user. Otherwise, we go on summing. Let's try this version. And we can see that it works. The do loop is tricky at the beginning. One is just to get used to it. For today, we have finished again. See you in the next video. In this video, we will talk about lists. We have already seen that they are data structure and how to write them, since a list program is built from nested lists. But we haven't really shown how to deal with them. Lists are a central topic in the Lisp world. The term Lisp is a shortening for list processor. We will see that they are often not very memory efficient, but they become useful for certain specific problems, like hierarchical data structures and viewing code as data, which let us change it as we want. But we should not run too fast. The first step is to learn how to work with lists. And now the hard truth. In Lisp, it doesn't exist a list object. Let's start an interpreter. We can verify it if we ask the type of a quoted list. The basic element is a cons, which is basically a pair. For example, we could create a cons whose elements are 1 and 2. The representation chosen by the Lisp interpreter are the two elements separated by a dot. This is also known as a dotted pair. Now let's assign it to a variable. We can see that a warning is shown because the variable x is undefined, but for the sake of the example, this is not a problem. If we evaluate x, we can see that we get the value back. We can get the first element in a cons using first. In the Lisp world, it is also known as car. To get the second element in a cons, we can use the function rest. The reason for this name will be more clear as we go on. In the Lisp world, it is also known as color. Now, what does this have to do with lists? Let's create a cons whose second element is another cons, whose second element is another cons, and we end it with nil. The Lisp interpreter reads what we have written, constructs an internal object that represents it, and then he has to choose an output representation. And we can see that in this case, the output representation is exactly the one of lists. The reason is that this is exactly what lists are. In computer science, they are known as linked lists. A list is a collection of elements which store some data and contains a reference to the next element. Let's assign the new list to another variable. This structure has many consequences. For example, it's really simple to add a new element in front of the list. We just have to cons the new value. We can see that now y contains the old list and in front of it the value we have just written. On the other hand, in general, it's expensive to add a new element in the end, because we have to traverse it. Moreover, to access the nth element, one has to start from the beginning and follow the references. Now it's also clear why the function which returns the second element in a cons is known as rest, because in general it contains a reference to another cons, which is the beginning of a new list. It is also interesting that we ended the list with a nil. It can also be represented as an empty list. Lisp provides a lot of functions for working with lists, the most simple of which are length, which returns the length of the list, reverse, which returns the list in the opposite order, and append, which takes some list and return a list whose elements are the concatenation of all the elements in the list we passed. It's important to note that those functions do not change the input values. Moreover, we have to remember about the cost of running them. For example, to know the length, we have to iterate over the whole list. In the previous tutorial, we introduced loops. We discussed do and dotimes. Lisp provides a for each-like loop to iterate over lists. It is known as doList, and it works as usual. For example, let's try to sum the element in a list. We can define a function SumList, which takes as input a list. We define a variable total, which is 0 at the beginning. Inside, we use doList, whose first argument is the name of the variable that will iterate over the list, which is the next parameter, and then, which is not mandatory, the return value of the loop. Inside, we just sum the value inside the total. Let's close the parentheses of doList, then the one of let, and finally the one of the function. There was a typo. The fun. Yes, this is not the more comfortable way of writing Lisp, but just for one example, we can do it like this. And finally, we can use this function. And it returns the expected value. We end up this discussion with a small consideration. Often people immediately connect Lisp with Lisp and conclude that Lisp is not an efficient programming language because it relies on lists, while for common tasks other data structures like arrays would be more efficient. This is not true. In Lisp we have arrays and hashmap as all other languages. Lists and the structure of the language are just an additional feature that make the Lisp family of languages unique. In this video, we will summarize 4 ways in which one can build lists in Common Lisp. Let's try to build this list. Our goal is that the Lisp interpreter doesn't return its value, but the list itself. If I just write it on the REPL and hit enter, we can see that the Lisp interpreter returns the evaluation of the list, but this is not what I want. The first solution is to use the quote form or the single quote mark. It is put in front of the list and it prevents the evaluation of everything that is inside this list. The single quote mark is a shortening for the quote form. This is equivalent to this. Everything that is inside the quote is not evaluated, and so the Lisp interpreter returns it as it is. Now suppose that the number 3 is not fixed, but is a variable. For example, we can build a function that takes a number and returns the previous expression, replacing the 3 with an x, and we quote it. we can see that the compiler already warned us that the variable x is not used. To understand what happens, let's try to run it. We can see that the quote operator also quoted the value of x and returns the symbol, but I wanted the x to be evaluated to its value. When defining this function, we cannot use the quote operator directly. One alternative is to build the list from its definition using cons. So we want a function that takes a parameter and return a list whose first element is the plus symbol. In this case I have to quote the symbol plus, otherwise it would try to evaluate it. And the rest is another cons whose first element is another list. Now we can end this list and we return to the previous one, and there is also a 1, and then it also ends. Let's run it this time. We can see that this is exactly what we wanted. The problem is that using cons it's really verbose. Another alternative is to use the list function. In this case, all the argument gets evaluated and then it returns a list with their value. In this case, we can define another expression and we make it return a list whose first element is the plus. Then there will be another list, and finally the 1. In the list of the products, we have to call the list function again. We cannot write it directly like this, because it would try to evaluate this list. To prevent this, we use again the function list. Again, this is the wanted value. Finally, we can use the backtick operator, which is the most common way of building lists in which we want to evaluate only specific forms. When we use it alone, it works like a quote operator. But we can use the comma to evaluate some specific forms. For example, in this list, I want everything to be quoted but the x, and so I put a comma in front of it. Again, this is exactly the result we wanted to obtain. Now, let's change a little bit the exercise, and inside the product, we don't want to have just one variable, but all the parameters that we pass to our function. With the backtick operator, it is really simple. Lisp provides us a way to group all elements that are passed to a function inside a list. Using the rest keyword, and then we can give it a name. We start by writing the list as we did before with the backtick operator. Now, inside the list, we can use the comma at operator, and basically it removes the parentheses of the list that we write immediately after. In this case, it is the list that contains all the arguments passed to our function, and so we basically have all the parameters passed to this product. Let's try to run it. We can see that it expanded all the arguments to the product. In the example we discussed, the backtick is probably the best solution, but all of the previous methods have their own application. The cons, which was the most verbose approach, is also useful for some specific application. For example, if we want to expand a list, adding an element in front of it, it's really simple using a cons. Or if we want to work with dotted pairs. If you don't know what a dotted pair is, I suggest you to go and look at my video on what are lists. Macros are one of the most powerful features of Lisp. In this video we will see what they are and what are the main differences with respect to functions. A function takes some input, runs a sequence of instructions and returns some value. It's important to observe that the function is executed after that all of its arguments are evaluated. We can see this fact if we define a function that takes a value and ignores it, and then we try to run it with an undefined variable. As we may expect, an error is thrown. A macro really looks like a function, because it is defined using defmacro and it is also evaluated as a list. But the actual evaluation is completely different. A macro builds and returns a form and expression. This first phase is known as macro expansion. Then it is evaluated. In particular, the arguments are evaluated after the execution of the macros, that is, after the expansion. Let's try to define foo as a macro. And we run it again. We can see that this time no error is thrown, because the macro foo built the expression 42 and then only the number 42 got evaluated. Now let's define the function plus f, which takes two arguments and return their sum. As we may expect, it returns the value, which is the sum. Now we make it return a list. If you don't know what the backtick operator is, I suggest you to look at the video for ways to build lists in Lisp. In this list, we want A and B to be evaluated to their value. Let's run it again. We can see that this time we have prevented evaluation. Now let's write a macro plus m with the same body as the function plus f. We compile it and we run it. We can see that this time the macro returned the same list as before, but after this phase, the macro expansion, the list got also evaluated. When debugging a macro, it's useful to look at its expansion. We can do this using macroExpand1. Which takes a list with the macro we want to expand. This is exactly the list before being evaluated. At this point, we have an idea on what macro are. The next doubt is, what are they useful for? What is their strength? The most common application of macro is the creation of some syntactic sugar or a full domain-specific language. Now, let's write an if that in one of its branch runs multiple expressions. So we write an if whose condition is true, so it will run the true branch. And in the first branch we want to put two different print. We know that we can't put multiple statements in the same branch directly inside the if. We have to use a progen form. If you don't know why, you should go and look at my video on branching inside Common LISP. Inside the progen we put two print. If we run it, we can see that it works. When we don't have a false branch, Lisp provides another form, when, that takes just a condition and the statement to execute if the condition holds. Which are the same as before. When is useful because it makes the code more readable. If we run this expression, we can see that we get the same result as before. When is a macro? Let's look at its expansion. We can see that behind the scene it just uses an if with a progen as we did before. Now I leave you an homework. You can verify that also cond is a macro. If you don't know what cond is, you should again go and look at my video on branching. You can verify that it uses if with macro expand. We end this video by writing a more complex macro. Suppose that in our code we have often to assign a value to a variable and then verify if it is nil or not. That is, we have to do something like assigning a value and then branching. X value is the value we want to assign to the x, while the true expression and false exp are the expression to do in case x is nil or not. It would be more convenient to introduce the form if let, which takes a binding, and then what to do in case x is not nil, and what to do if x is nil. We can do this with a macro. We define a macro if let, which take a binding, which will be a list with two elements, the name of the variable and then its value. What to do if it is not nil, and what to do if it is nil. Inside true expression and false expression, we could use the name of the variable we are defining inside the binding. And we basically build the expression we have written at line 1 and 2. In place of the name binding, we have to put its real value, what was provided by the user. This is the reason why we put a comma in front of it and make it evaluate. Inside we have an if. The name of the variable is the first element inside the binding list. Then we have the true expression and the false expression. Let's try to expand it. And this is exactly what we expected. I also leave you an homework. Write a macro if swapped that works like an if, but it takes first the false branch and then the true one. Let's make an example of expansion. When writing a macro, one should start by writing an example of expansion. Our macro if swapped takes a condition, the false branch, then the true branch, and it should expand to an if with the same condition, then the true expression, and finally the false expression. It's just a matter of building the list if with the two expressions swapped. In this video we will continue the discussion of macros we started in the previous one. Last time we have seen what are macros. Today we will go on comparing macros and functions. We have seen that when is a macro. But is it really required to be a macro? Could we get the same functionality using just functions? To be fair, we could. Let's define our own when, which is a function. It is fine if the condition is evaluated before the function is run, but we cannot pass directly the statements that we want to execute because they will have to be executed only if the condition holds. We can solve this problem taking as a parameter a function with the steps that one will have to run if the condition holds. Inside the body of our when, we call the function only if the condition holds. Inside trueFN, we have a reference to a function. We can call it using funCall. When we use this function, we have to put the body of the when in a function, for example using a lambda. As we can see, the result is what we expected. If the goal is removing the program we have to use with the if, this solution is not the best one, because we have to use a lambda instead. But we have shown that even without macros, we can prevent the execution of some arguments. We have also shown the function funcall that let us call a function when we only have a reference to it, not the symbol itself. It's interesting that funcall can be used only with function, not with macros, because they are not a function. Let's make an example. We define a function foof that returns the number 42. Then we define a macro that builds the same expression 42. We compile them. And we try to call them with funcall. In this case, we have the symbol itself, not a reference to a function, but we can build a reference using the sharp quote. Sharp quote make a symbol callable. As we can see with the function it works, but if we call the macro, it returns as an error that foo is a macro, not a function. We can conclude that most of the time that we need macros, we could use functions instead. Now the question is, when should we use macros? And the answer is rarely, especially at the beginning. Let's make some example on when they are useful. In the case of when, macros really make the syntax easier, thus it's a good choice to use macros. Another example is for performance reasons. Macros are expanded at compile time, or at most the first time that they are executed. Thus, one could use this fact to improve performance. I think about a web server that wants to produce HTML based on a Lisp form. One wants to create the HTML string one time at the beginning, and then just return it. The macros we have written until now directly return an expression. But inside a macro, we are writing a Lisp program, so we could do whatever we want. Let's try to write a macro that does some more computation than just returning an expression. For example, we can write myEnd that returns nil if all the arguments are nil. Otherwise, it returns the first argument which is not nil. MyEnd of a single expression is the expression itself. In fact, if a is nil, it is evaluated to nil, and if it is different than nil, it is evaluated to its value. MyEnd of two argument is the same as if the argument is different from nil, return the argument itself, otherwise return b. Or to be more precise, we have to return myEnd of b. This way we can generalize to more than two arguments. Let's try to write it. We define a macro, myEnd, which takes a list of expressions. Then we check if we have just one expression, then we return the expression itself. Otherwise, we build a list in which we verify if the first expression is different from nil, return it. Otherwise, we expand the macro itself on the rest of the arguments. Let's try to run it. If we call myEnd on a singular argument different from nil, it returns the argument itself. And even if it is nil, the value is nil. Now let's try to call it on two arguments. In this case, we can verify that it returns the argument itself, because it is different from nil. But if the first argument is nil, it returns the second one. Because it checked that this is nil, so I have to call myEnd on the expression with just the two. All the code that we write to build an expression, in this case, for example, the if length of expression is equal to 1, we call it the expander code, will only be executed at compile time. Thus, it will not affect the execution time of our program. The execution time will only depend on the performance of the expanded code. For example, in this case, calling length in a recursive function every time is not an efficient way of solving this problem, because we have always to traverse all the expression, but this is only executed at compile time, so in this case it is fine. For today this is all. Let me know in the comments if you liked the video, leave a like and subscribe. Bye! We defined the iflet in a previous video. It bounds the value of a variable, and then, if it is not nil, it enters the first branch. Otherwise, it takes the second one. Those two implementations behave almost the same, but I think that the first one is better, for at least two reasons. In the parameters, we can see the structure that it expects. For example, the binding is inside parentheses. Moreover, the body looks like the form that will be created. This is why we are going to explore more in detail what we can do with macro parameters. When working with functions, one can simply list the name of parameters during the definition of a function. For example, this is a function which takes 3 arguments and returns a list with those 3 arguments. Then, when we call it, the number of arguments is equal to the number of parameters we declared during the function declaration. Each argument will be bound to the corresponding parameter. If we call the function with the wrong number of arguments, an error is thrown. Function definition is actually much more flexible. Lisp let us extend the schema we described before with 3 symbols: optional, rest, and key. With optional, we can declare arguments that are not mandatory. For example, we can make C optional. In this case, we can call the function with 2 or 3 arguments. The value of arguments that are not provided is usually nil. But we can change it by providing a default value. Like this. With rest, we can write a function in which the number of parameters is not known beforehand. Like plus, you can call it with as many arguments as you want. In this case, all the arguments are grouped in a list. Params is a list which contains the number 2 and 3, which are the second and the third argument. Finally, there are keyword parameters. Suppose that you have a function with 3 optional parameters, and most of the time you want to call it with just a single argument. None of the previous methods would help you. For example, we would have to write all the arguments as optional, and then if the one with nil value is C, we have to pass nil to both the first and the second one. A better approach is to use the key symbol. And for example, if you want just to pass C, we have to call foo like this. Foo with value for C equals to 3. As before, we can provide a default value using a list with the name of the parameter and its value. For example, if we want to provide the default value for A, we would do like this. With macro, we have even more freedom. Let's start from the letIf macro we have already defined in the previous video. We know that the false branch in an if is not mandatory, so we can generalize our iflet by making the false optional. But the most inconvenient parameter is binding. Common Lisp let us define nested structures in parameter, so we can write directly a list of 2 arguments instead of binding, and then use those values inside the definition. When we call the macro, Lisp verifies that the first argument provided is a list, and then it looks at the binding inside. This is known as destructuring. It's really convenient. The macro becomes easier to read, and we have even a check when we call it. We can see that if we try to call it without a list as the first parameter, an error is thrown which tells that the element provided does not satisfy the list requirement. Alice and Bob work at the same Lisp project, and they both have defined a function named main. How can they be sure not to have name clash? The most clean solution are packages. Packages in Lisp are similar to namespace in C++ or packages in Java. At the beginning, we can assume that we are working alone, and so the name we choose for a variable are probably not going to create conflicts. But this is not a good way of dealing with the problem. We don't know who will use our software in the future. The correct solution is to limit the scope of our symbol and defining what we are using from the outside and what we want the other to use from our definitions. A package is a set of symbols. The symbols that are intended to be used by others can be exported and imported in another package. Every time you interact with a Common Lisp, you are in some package. We can verify which one it is with the package variable. One of the main differences from other languages is that in Lisp, packages are object as everything else. We can verify it using type of the current package. In Lisp, a symbol that starts with the colon is a keyword, and it is automatically put inside the keyword package. As we can verify with, we check if it is equal, the keyword CL with keyword. This is how we can access a symbol inside a package. First we put the name of the package, then a column, and then the symbol we want to access. Moreover, inside the keyword package, a symbol also defines a constant with the same name and value. This way, we can use keyword as function parameters without quoting them. We can see that CL and CL quoted are the same. The function describe is useful to get more details about a symbol. For example, we can see that in the current scope, the symbol AND comes from the Common Lisp package and is a macro. The Common Lisp package, or :cn, is the package that contains all the standard functions, macros and symbols. By default, when we open the REPL and define our own symbol, they are put inside, or more precisely, they are interned inside the Common Lisp user package, as we have seen looking at the value of the variable package. We can change the package we are currently in using inPackage. As we have seen before, we don't have to quote the keyword CL, we can use it directly. Now we can verify that the value of the package has changed. We can define a new package using defpackage, to which we pass the name of a package. At the beginning, we have to define if we want to import some symbol from other packages. Usually, one would start by importing the CL package. Then we move this file inside the new package. And finally, we can define our function. Now we can see that if we try to call this function, we get an error. Because the function test is not defined inside the Common Lisp package, which is the one in which we are currently with the REPL. We can call a function inside a package regardless of whether it has been exported using the double colon. The first part is the name of the package, double colon, and then the name of the symbol. We should never use the double colon. The correct solution is to export the test function and then call it using a single colon, as we did before with keyword. Inside a package, we could have some functions that are not meant to be used by other and only for internal purposes. We can define what the other can use inside our package using export and then the name of our function. Now we can see that we can call test even with just a colon. Finally, we can access all the symbols in the package by changing the package we are currently in. And then we can use the symbols directly. The usage of use is discouraged. It should be used only with standard libraries. Otherwise, one should always import only the symbol that is strictly needed with the import from keyword. For example, let's define a new package that imports just test from com.example. Using the import from keyword. We change the package we are in. Now I can define a function that uses the test function in the other package as if it were in the current one. Now I can access test2 using the double column or exporting the simple and then using the single column. We conclude with a bonus tip. All the symbols that start with a colon are interned in the keyword package. Sometimes we don't want this to happen, to keep the keyword package more clean. To prevent a symbol to be interned, we can use a sharp in front of it. For example, all the name of functions in the import and export will not be used often, so we don't have to intern them. And so we can put a sharp. As usual, tell me in the comment if you liked the video, leave a like and subscribe. Thanks for watching. This is a possible definition of a macro that implements a for loop, and we can see that it works. The I assumes all the values from 0 up to 10 excluded, and for each it runs what's inside the body of the for loop. And it could go on working for ages, until someone tries to write something like, in this case, it doesn't print anything and it just throws an arrow. Writing macros is difficult, for a variety of reasons. For example, because there are two layers of execution. There is the expansion and then the actual evaluation. What we see here is another complexity, which could be a little subtle at the beginning. We built a for loop using a do one. We take the name of a variable and we use it as a variable in the do. And it goes from the value of the variable from to the value of the variable to. At each iteration, we increment the value of the variable by 1. If you are wondering why we're using another variable limit and we didn't put directly the value of 2 inside the condition, this will be the topic of another video. Now let's try to do the expansion of the last form we evaluated by hand. The name of the variable is limit, which goes from 0, is incremented by 1, we can see that there is a name clash with the symbol limit. One is defined inside the macro, while the other is defined in the outer scope. The problem is that the symbol's name are evaluated in the calling environment. When we call the for, it will be replaced by this expression, and so the value of each variable is defined inside the function or the form that called the macro. Sometimes this is a powerful feature, but most of the times it will lead to some weird bugs. Every time we introduce a new variable, we could fall in this error. Not all variables' definitions are a problem, but every time that we have one, we have to pay attention. We could try to solve the problem by using a sufficiently complex name in the for macro, but this is not a good solution, and it would have problems anyway as soon as we try to use nested for loops. The definitive solution is to use the function gensym. We can see that it produces a symbol name that has never been used and will never be used again. And we have to use this name instead of the limit one. Thus, a better implementation for the for loop macro is to use a let binding to get a new name. This is the symbol for 2, and we get its name using gensym. We return the same value as before, but this time we use the symbol sim2 here and in the condition. Let's try it again. And we can see that this time it also worked for limit, and it would work for any symbol that we put inside the for. We have seen that a wrong usage of captured symbol can lead to very subtle bug, and we have shown a possible way to solve it. For today, this is all. Thanks for watching. Let me know in the comment if you liked the video, leave a like and subscribe. Can a function behave differently depending on the parameter it gets? Yes, in Common Lisp we can use CLOS, which is Common Lisp answer to the need for dynamic object-oriented programming. To create different kind of object, we have to build classes. In Lisp, a class has a name and it's characterized by a set of properties called slots. We are not comparing these to other languages yet. In this example, we have a class circle with a property radius. The init keyword lets us specify how to set the radius during construction. We can create a new instance of this class using the function makeInstance and pass in the class name as a symbol along with all the slots we want to set. In this example, we set the radius. We can verify which is the class of an object using the class_of function. In this example, my circle is an object of the class circle defined in the Common Lisp user page. We can access and set the value of a slot at any time using the slot value function. We can verify that the current radius is 10, then we set it to 20, and we print it and verify that it is 20. To set, we use the setF function of Lisp. We can define a more convenient function to read a slot using the reader keyword inside the def class expression. In this example, we don't have to use a slot value, but we can use directly the radius symbol. We can even define a function to read and write using the assessor function. For the moment, we are not writing custom functions that allow more fine-grained checks, but even when we will, Common Lisp doesn't have visibility modifiers. Using slot value, we will always be able to force a value into a slot at our own risk. This is similar to what happens with packages using single and double colon. You can look at my video on packages for more details. We can provide a default value for a slot using the initForm keyword. In this example, if we don't provide a value for a radius inside the makeInstance, it will be put to 0. InitForm can also be used to make a slot mandatory. We just have to throw an error if it is not provided. A class can take all the slots of another and add new slots. This is known as inheritance. We can write a list of classes from which we want to inherit between parentheses in the definition of that class. Even if not stated, all the classes inherited from the class big T by default. As we can see, we can create a class colored circle and we can access the radius from the parent. By the way, have you ever heard of UML? It's a standard way of visualizing class hierarchies. And yes, CLOS plays nicely with UML. In the same way, we can create a class for a rectangle, which is characterized by the base and its height. Then we can create a new class for a colored rectangle, which is a rectangle with another slot for the color. But hold on a second, it seems redundant and repetitive, doesn't it? We did the same for colored circle. CLOS has a better solution. A better approach is to create a class, colored circle, and then make all the other classes inherit from it. colored object as just a slot color. Then we can create a colored circle by inheriting from circle and colored object. In the same way, we can create a colored rectangle by inheriting from rectangle and colored object. This shows that a class can inherit from multiple one. This is known as multiple inheritance. We end with this diagram. Now we see how to create functions that behave differently depending on the parameters. They are known as generic functions. We can define a generic function using defgeneric. At the moment, there is no body for this function. At most, we can define some annotation, like a documentation string. If we try to call a generic function at this point, it will fail because it misses an implementation. We can implement a generic function for a class using def method. We have to specify which class each parameter should accept. In this example, we have just one parameter, shape, and for this particular implementation, it has to be a circle. And we can compute its area as pi r squared. If we call the area if we call it on a circle, it works. If we call it on a rectangle, it fails, because we haven't implemented the area function for a rectangle yet. We can even call the function area on the object greenCycle, because it is an object of the class coloredCycle, which is a child of the class circle. Finally, we can define the area method for a rectangle, and now it works also for a rectangle. Let me know in the comments if you enjoyed this deep dive into CLOS. Leave a like and subscribe. Until next time, happy coding! Polymorphism is probably the most interesting feature of object-oriented programming. We will start by showing what are multi-methods and what we mean with multiple dispatch. Then we will see a classical application of polymorphism. If you haven't seen the introduction to CLOS, I suggest you go and check it out first. In this example, we have two hierarchies of classes: Avatar with two children classes Warrior and Wizard, and Weapon with two children classes Sword and Magic Stick. We can see that we haven't put any slot. The idea is that we want to focus our attention on generic function and methods. Then we define a generic function makeAttack. It will take as input an avatar and a weapon. Then it prints the result of the attack depending on the avatar and the weapon. We know that warriors are good with sword, but not so much with the magic stick, and the wizard is the opposite. If we call makeAttack passing as first parameter an object of type warrior and the second as a sword, it will print that this is a great physical attack. On the other hand, if the avatar is a wizard, it will be a bad physical attack. And so we list all the four possibilities. Then we create some object of those classes, and we try to call the previous method. We have var, which is a warrior, viz, which is a wizard. Moreover, there is the big sword, which is a sword, and old stick, which is a magic stick. And we call makeAttack with all the combination. We can see that when we call the function, we get different results depending on the parameters. We haven't written any conditionals. CLOS did it all by itself. This is a simple application of polymorphism. The result of the function depends on the type of the objects. Moreover, CLOS implements multi-methods. It looks at the type of all the parameters. Most other programming languages implement polymorphism just on the first one. Now we define a class ApprenticeWizard, which inherits from wizard. CLOS will, by default, look for a method that can be applied. If there are multiple ones, it will choose the most similar one. In this case, we have Junior, which is an apprentice wizard, and Old Stick, which is a magic stick. So when we call makeAttack, it will choose the method which takes a wizard as first parameter and the magic stick as second. And as a result, this will be a great special attack. We can specialize methods even more. In the language of object-oriented programming, this is known as override, which means that that we make a child class do something different for a method already implemented for the parent class. In this case, we make attack specialized for an apprenticed wizard and a magic stick. And we print I'm just learning. We run the same method as before. This time the result is I am just learning. We have prevented the method from calling the one from the class wizard. Often, when we implement a method for a child class, we want to call also the parent anyway. In Lisp, we can call the function callNext method. CLOS is that there is a method for an apprentice wizard and start to execute it. When he meets the callNext method, he calls another method which satisfies the parameters and is again the most similar one. In this case, we start by calling makeAttack with an apprentice wizard, and then callNext method will call makeAttack with a generic wizard and a stick. By default, callNext method is called with the same parameter as the current method. When we try to print a method, we can see that Lisp chooses a not so nice string. We can improve it by overriding printObject and implemented this generic function for our own class. We can see its parameter from the standard documentation. PrintObject takes as input the object we want to print and a stream. We want PrintObject to take as an object an apprentice wizard and then any stream. Then we just use a format. If the class had any slot, we should put them. For the sake of example, we just print the string I am an apprentice. If we try to print again a representation for an object, we can see that for an apprentice wizard, it prints I am an apprentice. For today this is all. Let me know in the comments if you liked the video, leave a like and subscribe. You can pay as attention as you want, but your program will probably have some cases in which it doesn't work. Today we'll see how to look for potential problems inside our programs. Debugging is the process of identifying and removing errors from computer software. The first strategy, which is really common in other programming languages and we can also apply to Lisp, is to put print everywhere in the code. In particular, I want to pay attention to a specific feature of print. It returns whatever you pass him as parameter. For example, if we wanted to print n in this case, we would have to introduce a prog_n, and first we print n, and then we also return n in this branch, not to change the behavior of our function. But we don't have to, because print n also returns the value of n. So when we are here, we just have to write the print and wrap the n. We can see that it printed all the times that we passed for a value of n which is less or equal than 1. When we write code in a functional style, our function will be a single expression. This is the reason why this feature of print is useful. With the trace function, we can see every time some specific function are called, with which parameter and what is the return value. For example, we want to trace fib. We just have to call trace with the name of the function. If we call trace without parameters, we get the list of currently traced functions. Let's try to call fib again. We can see that to call fib of 5, we called fib of 4 and fib of 3, and so on for all the others. When we are finished with tracing, we can use the function untrace to make it stop tracing our function. And next time that we call fib, the trace is not shown. We still have the print of n, but now we can see that only the result was printed. Trace is like some automatic print in strategic positions. Then we have break. that allows us to put a breakpoint in the code. For example, I can put a breakpoint at the beginning of fib. When we run our software, it will stop as soon as it will reach our break, and at this point we will have a REPL. We can see that we get a REPL similar to when an error occurs. In the backtrace we can see all the functions that have been called, and if I press continue with 0, we can see that the code goes on. Fib of 5 called fib of 4, which calls fib of 3. At each stage of backtrace, we can inspect the local and global variable. Pressing enter, I can see that currently the only local variable is n equals to 3. We can press V to view the source code we are currently in. We can step between form using S. The problem is that by default, SBCL optimizes a lot the code. During the debugging, it's useful to set the debug level for optimization. To do this, we stop the debugger, pressing Q. We add the declaration in which we set optimize to debug. We compile again the function and we start it. We can see that while we step, I am pressing S, we get more details on which form got evaluated. Pressing E, we can evaluate a form in the current frame, in the current context of the function. For example, n, I can see that is equal to 2. It is interesting that break is an expression, so it's really simple to introduce conditional break. Just put it inside a branch like when. For example, I could have noticed that my function behaves in a strange way when n is small. So I put the break only when n is less than 3. Then even if I call fib with 10, the execution went on until we reached fib evaluated on 2. Inspect is one of the best ways to explore the state of our objects. Sure, you can print the values you are interested in, but what if you could have a visual representation of the internals of your objects? For example, I define a class rectangle with 2 slots, and then we make an object of rectangle, base 10 and height 5. Let's evaluate it in the REPL. Then I click on the object and press Ctrl C, Ctrl V, Tab. If there were some nested structure, I could dig into all of them. Every time an error occurs, we get a shell that allows us to view and inspect the state at that point. This is usually sufficient to understand what's wrong in our program. If you cannot, you can trace or break into the code. More advanced techniques exist, but they require more deep understanding of the condition system. So, they will be a topic for a future video. For today, this is all. Let me know in the comments if you liked the video, leave a like and subscribe. The condition system is the way in which Common Lisp deals with errors. Let's write a function factorial which computes the factorial of a number. and then a main which calls it. And we can verify that it works. The factorial only exists for integers greater or equal from 0. But if we try to call it with a negative number, we can see that our function crashes. It would be better if we could make factorial signal to the caller that the factorial doesn't exist. In other programming languages, there are two approaches. In languages like C, we return a value that is not a valid factorial, such as -1. When the caller sees this value, it knows that it cannot be a factorial, and so there must have been some errors. In languages like Java or Python, we throw an exception. The execution gets interrupted, and the control returns to the caller function. If it manages the error, we end here. Otherwise, we pass control to the caller of the caller and so on, until we reach the top level of the interpreter, and so the software crashes. Exceptions are great because are a very general tool. The problem of exception is that in the function in which the error occurs, we cannot usually manage the error. For example, if we want to show an alert, it depends on whether this is a command line application or a website. On the other hand, the caller of the function has completely lost the context of the error. We'll see that Common Lisp generalizes the second approach, the exception one, in its condition system. The condition system is composed of 3 steps: the signal, the handlers, and the restart. The signal is emitted as soon as the error condition occurs. If the number is less than 0, we have to signal a condition. We replace the if with a cond. Let's run the main again. This time we can see that the execution is interrupted exactly where the condition was signaled, inside the factorial function. We can see it inside the backtrace, and the error is more meaningful. At the moment, we can just retry the execution or abort it. We underline the fact that the stack is not unwinded. We are exactly where the condition was signaled. This is completely different from what happened with exceptions, where as soon as the exception gets signaled, the execution gets passed to the caller function. In Common Lisp, we can look at the current stack trace and inspect all the variables. For example, inside the factorial, we have the variable n, which is -42. We'll come back later on these windows. For the moment, let's look at the condition. I abort the execution. We would like to be able to recognize the condition that was signaled from the caller function. The problem of the current approach is that to understand what happened from the outside, we would have to compare strings. That is the message that we passed to the function error. And this is not a good solution. The right solution is to introduce CLOS. Conditions are organized in a hierarchy like classes. We can define new condition using define condition. Define condition is like def class. It takes a name, some parent classes. Conditions are a really general system which let us pass not just error, but any kind of objects. For the moment, we just want errors, so our condition will be subclasses of error. Moreover, we can have some slots. For example, a test with the error message. Define condition is slightly different from def class. For example, we have to define a reader. And now we can write this condition using error and passing a symbol with the name of the condition. If we run the main again, we can see that the condition raised is of type negative number. There are some predefined conditions, like division by 0, which is raised when we try to divide by 0. Division by 0 is a subclass of arithmetic error, which is a subclass of error. Inside our program, we don't want to see the debugger, but our functions have to be able to manage a condition by themselves. The first thing we can do is basically what Python and Java offers. We want to be able to catch a condition from a color function. In Common Lisp, we can get this result using handle case. So we put it inside the main. Handle case takes the statement to run, and then list with all the errors we want to manage. For example, we are just interested in negative number. This is basically a function, and we want to print the error message. Inside the handler, we have a variable NNE, negative number error, which is a reference to the condition, and we use it to read the tests which were passed by the signal. We can see that this time the debugger hasn't shown up, but the error was managed by the handle case. But what if we can fix the error by degeneralizing the factorial function? For example, the factorial of a negative number may be the opposite of the factorial of the absolute value. So the factorial of minus 42 could be minus the factorial of 42. To get this, we have to introduce a new concept, a restart. The goal of the handler will be to call the right restart. So let's remove handler case for the moment. Instead, we put a restart case directly inside the factorial. Inside the restart case, we put cond. And as secure argument to restart case, we offer a way to restart the execution if an error occurs. We call it use absolute value. This doesn't have to be a class, it could be just a symbol, like in this case. And when use absolute value is called, it just returns minus the factorial of minus n. Let's compile the function and run the main again. We can see that this time the debugger appeared again. But we have one more option. We can use the absolute value. Let's try to run it using 0. And as we can see, the execution finished successfully. Now we have just to tell Common Lisp to call use absolute value by default. Instead of handler case, we have to use handler bind and invoke restart. Inside the main, we put an handler bind. Handler bind takes a list of conditions and what to do if they occur. For example, if a negative number is signaled, we want to invoke the use absolute value. This is a function and we usually pass a lambda. It takes as input the condition and it invokes restart. In particular, we want to invoke the use absolute value restart. We put the condition because we can have it, but in this case we don't use it, so we declare it as ignore. This way we won't have some warning telling us that we are not using C. Now let's run the main again. I haven't put the format inside the handler bind. Let's compile and run it again. And as we can see, this time the function call chosen the restart by default. Today we've explored the main feature of the condition system of Common Lisp. Is this all we can do? Absolutely not, but the rest we'll have to wait for another video. Let me know in the comment if you liked the video, leave a like and subscribe. In JavaScript, we can declare a dictionary like this. This basically became JSON standard because it is convenient, easy to read and write.
Common Lisp has built-in support for hash table using a syntax like this, in which make hash table create the hash table, and then with getHash you can read and write keys. Is it good enough? Absolutely not. This is a low-level primitive, but we have macros, and so it's really simple to improve the syntax. Hash tables, also known as dictionaries, are everywhere in real-world projects. Many languages use dictionaries to represent objects. In Common Lisp, we have the more structured CLOS, but the usage of dictionary is quite common. For example, in the web environment, the most common usage is for import and export JSON objects. But this is not the only usage. Algorithms often need mapping from an arbitrary set, not just integer, for which we could use vectors. A common library to parse JSON object is JSON, and we could also use it to create dictionary literals, like this. Let's create a new package in which we load JSON. We can see that now person contains an hash table with exactly 3 elements. This is surely more convenient than using makeHash table and getHash, but we could do even better. Alexandria is the most common util library for Common Lisp. It has a feature. It is minimal and it contains only essential utilities. It is portable and it does not contain functionalities provided by other common used packages. Nevertheless, it contains a lot of functions useful for working with dictionaries, and in particular we can already improve the syntax for dictionary literals using a list hash table. An a list in Common Lisp is a mapping based on lists. It is a list of conses. The first is the key and the rest is the value. It is useful when you want to build small lookup tables, but if the size grows, also the performance really degrades, because every lookup takes a linear amount of time. We can use a list hash table as a dictionary literal. We have to import Alexandria. And then we can use it. As usual, we have created a hash table with 3 elements. Alexandria also provides other useful functions, like hash table a list, which is the opposite and can be used as pretty print. In general, Common Lisp just shows the name of the object, and if we want to look inside it, we have to use the inspector of life, for example. But one could also use hash table a list, and it allows you to inspect the key and values stored inside. Hash table keys is again useful to get the list of keys. Ensure getHash is like getHash, but allows us to provide the default value if the key does not exist. Alexandria is an interesting project, but as we said, it's really minimalistic. Based on it is born the Serapeum project, which adds again a lot of function for dealing with dictionaries, and in particular there is the dict construct. In the previous example, since we are using string L keys, we had always to specify the comparison function. Dict already sets the correct default. We have to include Serapeum. Alexandria and Serapeum are built to be used inside the global environment. So even if we put them inside the use, we should not have any conflict with the standard library. But I prefer to have them in their own namespace. We can see that it built the usual table with test equal and 3 elements. From the function provided by Serapeum, it's interesting toggle pretty print hash table that override the default output for dictionaries. Instead of the name, it prints the content. It's also interesting the href function, which can also be written as @ that allows reading from keys. If we add nested dictionaries, we could use at and provide all the path. In this case, best known for is an array, and so we can't index it the same way because it only supports hash tables. If you use a lot Common Lisp, I suggest you look at those libraries. The main issue of Serapeum is that it is quite fat, and we still need some specialized libraries for specific tasks. The rutit package is a small utils library that provides a lot of useful utilities for a variety of tasks. In particular, some deals with hash tables. Let's import rutils and enable the custom syntax. From now on, we can declare dictionary using the #h macro. We can see that this is different from the previous approach. This macro does not follow the usual syntax using parentheses. What is used is a reader macro. A reader macro allows the software developer to change the syntax of Common Lisp. In particular, it was changed what happens when we write #h. We still have the prettyprint enabled, but we can see that this is the usual dictionary we declared above. Again, we have a lot of useful functions, and in particular, we can enable toggle prettyprint hash table. This is similar to what we got previously with Serapeum. The idea is that if I'm using rutils, I don't use Serapeum and other specific libraries. So if I don't have Serapeum, I can enable a prettyprint of hash table using toggle prettyprint hash table. And now, if I show person, I can see that it uses a custom syntax. The sharp braces is the same as the #h parentheses. In this video, we've introduced some really common libraries in the Common Lisp world. It's really worth exploring them if you need to write some serious program using Lisp. The fact that Lisp is a fixed standard doesn't mean that the language is dead and has stopped evolving. It just means that all the libraries that are based on the standard Lisp will go on working as long as there is an implementation of the standard. This video wanted to be an introduction, so I used string as keys, but it's really common to use keyword instead. Nevertheless, the comparison of string and keywords has to wait for another video. Let me know in the comments if you like the video, leave a like and subscribe. Types really help the developer prevent bugs. Common Lisp is a dynamic language, but it has a type system, and today we see how it can help us track and trace bugs. I call this discussion built-in type safety, because we can take advantage of it with the default installation of a Common Lisp compiler. The following example will all use SBCL, and we start with maximum safety and minimum speed. In Common Lisp, you are not required to specify type when declaring a variable, and a symbol can hold values of different types at different times. That is, it is a dynamic language. You are not required means that if you want, you can, and the compiler will be able to optimize the code and provide more warnings. Deducing the probable type of a variable during compilation is known as type inference. This enhances the ability to catch type-related errors early in development process, providing an additional level of safety without explicit type annotation. During this discussion, we will use this implementation of the edit distance in Common Lisp. Let me know in the comments if you are interested in more details about this particular implementation. This is a common problem in many areas, from natural language processing to coding theory, and it is also often asked in interview processes. In particular, we will compute the edit distance of two very large strings. We have a file, DNAs, which is 20Ks. That is, it contains two strings of 10Ks. We will pass those strings to dist and see how much time it takes to get executed. Make array by default accepts elements of any type. In memory, it basically just stores pointer to the actual value, since each cell could have different size. But if we provide the element type, it can optimize the space, for example by storing the actual value inside the cell, and the reference time. For example, since we read the value directly, we use better the cache memory. This is an example of dynamic programming, and inside dp, I know that I will only store integers and that will not be too big. For example, I expect them to be less than 2 to the 16. Let's try to run as it is now. We can see that it took more than 3 seconds. Now let's change the code and provide the element type to make array. Compile it again. Let's try to run it. And we can see that this time it took only 1.8 seconds. What we've seen is not enough. Common Lisp is a compiled language, and so we can take advantage of it to get more warning before execution time. During compilation, we get a lot of errors like missing arguments, missing functions, syntax errors, and so on. Nevertheless, SBCL is quite smart and during compilation can provide a lot of type analysis. Let's see an example. This is the same function as before, but I've introduced an error. Let's try to catch it. I compiled the function, and we can see that a lot of errors appeared. Let's see the first error. This is just a warning without many information. Let's look at the second. In this case, we can see that Common Lisp has the dust, the type from is a number. But we are providing here a sequence, a string. Why is that? The previous time I used the form, I used it directly inside 1+. I forgot to use the function length. And so, from this expression, Common Lisp could deduce that from is an integer. And so, if I use here as an integer, I cannot use it after as a string. It would have been better if he just said me that I cannot use from there as a string. But Common Lisp cannot know that I want from to be a string. I've never said it to him. So he can only build assertions from previous code. I can improve this fact providing a declaration. Let's compile it again. And we can see that this time the error is exactly on 1+, because from is a string, but I am using it in place of a number. Let's fix the code, and we can see that all errors disappeared. But what if the input is safe? In Common Lisp, we can also add type safety during runtime. The main issue is that all the checks we do during runtime will slow down the software. Developer can choose to include explicit runtime checks for critical sections of the code, striking a balance between performance and safety in specific code segments. What if I know that the input is trusted and I just want a lot of speed? So, in this case, we can just change the declaration. For example, we want maximum speed and lowest possible safety. Let's try to run this inside our code. Let's return to the first version. And let's try to compile it. We can see that many errors appeared. For example, in this case, he is unable to optimize because he does not know the type of from. And so there must be some dynamic dispatch based on the type of from at runtime. But we know that from is a string, so let's tell him. Let's compile it again. This time the error is on a rep of dp. That is when we read the value inside the dp. Again, in this case, he cannot say that this is a number. We have to tell him. Let's compile it again. And finally, we have this error, because the type of from is still too large. He wants a simple array. So we declare from a string a simple string. Let's compile it again. And we can see that all errors have disappeared. Now let's try to run the code again. We can see that this time the code executed in 0.56 seconds, which is much less than before. It's interesting that since we have set speed to 3, the compiler has told us some hints to make the code faster. It's important to never use this setting for application we want to distribute. In general, it's always better to have more safety and only optimize what is strictly needed. As usual, in Common Lisp, you have complete freedom in what you can do. This will be even more clear in the next video about algebraic data types. We have seen that, despite being a dynamic language, in Common Lisp we can have a lot of warning and hints on type safety during compile time and runtime. Moreover, we have to choose if we want slower code with checks at runtime or faster code without checks, all just by setting some declarations. For today, this is all. Let me know in the comments if you liked the video, leave a like and subscribe. C is not just a programming language, it is a protocol. Most high-level languages have some form of foreign function interface that lets the programmer call a library that exposes a C function. In particular, this is true for most Common Lisp implementation. I talk about implementation because this is not part of the Common Lisp standard. From the point of view of Lisp, the underlying system doesn't exist, even though sometimes it's useful being able to talk with it. The CFFI package is the de facto way of using FFI in Common Lisp. It unifies all the standard Common Lisp implementation, like SBCL, CCL, ECL, and so on. In particular, we will pay attention to SBCL, but the interface is the same. To be able to call a code that exposes a C function from an higher level language, we need a binding. That is, some glue code that tells the high-level language how to pass data to the C function and how to read it. If you have ever done it in some other languages, like the Java native interface in Java, you may know that you have to write some glue code in C. The idea is that Java provides an SDK for C that allows you to manually manage a Java object. This way you have enough control to provide data to the C function. In Common Lisp, we write the binding in Common Lisp directly. So, the first step is learn how to deal with G memory from Lisp. In C, we don't have a garbage collector, so every time we allocate some memory on heap, we have to remember that we have to free it. The same holds for CFFI. We have the function foreign alloc, which takes a parameter and returns a pointer to the memory in which we can read and write. A pointer is basically the address of a memory location. I create a new package in which I load CFFI. The first step is to understand how to manage memory, how to allocate it, how to free it, and how to read and write. The easiest way to allocate memory is using foreign alloc. We can see that the first parameter is type, which can be any of the standard type in C, like int, unsigned int, char, and so on. For example, we want to allocate an integer. From the type, CFFI understands directly how many memory he has to allocate. When we have finished using a memory location, we have to free it, using foreign free. Using foreign type size, we can understand how much memory is required for a specific type. For example, on this system, an int takes 4 bytes. Keeping track of dynamic memory in C is difficult, but in a language with signals, it's even more. The risk is to allocate memory at the beginning of the function and free it in the end, but in the middle, an exception is raised. The solution is to use with foreign pointer, or its wrapper with foreign object, which does an unbind protect. That is, it catches the exception and frees the memory. We can see this inside the code. At the beginning, there is a foreign alloc, then The body of the function is executed inside an unwind protect. In the end, everything is freed. It's interesting that the code for SBCL tries to understand if the size is constant, and in this case it tries to allocate on the stack. Now we've seen how to allocate some memory. The next step is being able to read and write inside that memory location. Let's allocate some memory again. We can refer to a memory location using mem_ref. Pointer don't carry type information, so we have to specify which type we are reading and writing every time we access a pointer. We have never written any data inside this memory location, so reading it now is undefined behavior. This is some value that was present in memory when we allocate it. Before reading, we have to write it, for example using setf. Now, if we read it again, we can see that we found exactly the same value. We have to be consistent when we allocate, read and write data. For example, the type float has the same size as an int. But it does not make sense in general to write an int and read a float. Even though, if we don't pay attention, we could do that. We can see that no error is raised, even though the value does not make any sense. So we've seen how to allocate some memory, how to read and write inside that memory location, and how to free it. After that I free a memory location, I must not write it again. If I need some more memory, I have to allocate it again. Foreign alloc also take a count parameter that specify how many contiguous memory location I need. It basically let us allocate some array. For example, this is the way in which we can allocate an array of 10 elements. Let's store the address in a variable. We can access each cell using mem_ref, which takes as an optional parameter an index. For example, we are modifying the third cell. Index are based 0, 0, 1, 2. We have always to specify the type. Let's look also at an example on how to use with foreign object, which, as we've seen before, links the lifetime of an object to the scope of a variable. For this, we can take an example from the official documentation. We can see that we are declaring an array of 10 elements at the beginning. Then, inside the scope of this variable, we iterate over each element and we assign it a random value. Then we iterate again and we show all the values. In the end, the object will be freed, even though we don't have to do it manually. Dealing with C is always difficult, but CFFI is a powerful tool. There are a lot of well-known and tested libraries that you can use inside your Lisp program. For today this is all. The next step is to try to actually link a library. Let me know in the comments if you like the video, leave a like and subscribe.
One can do object-oriented programming in Common Lisp using CLOS. But what if it is too much? If I don't need polymorphism and inheritance, I really just an object, which is something that stores a state and can do some operations. In this case, I can just use functions. Our goal is to create a really simple object that just counts. Every time we call it, we get a bigger value. In this example, we declare a variable c, which is an instance of counter in a let, and then we call 2 times c. We have to use funcall because this is a variable and Common Lisp is a Lisp too, as we have seen in a previous video. One may think about using a global variable. For example, I declare a variable count, and then inside the counter function, I increment it. This solution is not good, for example, because I can't have multiple counters at the same time, because there is just one global variable. The variable should be strictly connected with the object, and if I create multiple objects, each should have its own counter. The variables introduced with let are lexical scoped, which means that they can be used only inside the block of code in which they are defined. For example, here we have an x, and we can use x only
before the close parenthesis. Outside of this block, x does not make any sense. Or there could be other x declared, but are not these x we have declared here. This may seem obvious, but it is not. For example, defvar follows a different rule. Moreover, in a let, the last expression is returned. For example, we can see that here we have a function foo, which declares a variable x, and it is defined in this expression. When it gets evaluated, 1 plus 42 is 43, and 43 is returned as the return of the let, which is then the return of the function. This is a really well-known trick, which in the Lisp world is known as let over lambda, and allows us to create what is known as a closure. We have a function counter. Inside we have a let with a variable count set to 0. Count makes sense inside the scope of the let, which is the lambda, but lambda is just the definition of a function, and so it gets returned without executing it. When we run the function counter, the result is a lambda function, which is set to, in this case, to the variable counter. In this case, I've used the same name for the variable and the function. In Lisp, this is completely fine, but we can use different names just to prevent confusion. In the end, the variable counter will contain a lambda function, which has inside a reference to the variable inside the old let. So Common Lisp cannot free the variable count which was inside the let when we executed the function, because we still have some valid pointer to that value. The result is that now the variable counter has its own state, which will be defined as long as we don't lose a reference to the lambda function. If we run this code, always remember to use funcall, because this is not inside the function namespace, but in the values namespace, because it was defined with defvar. But the result is exactly what we expected. If we have multiple counters, they do not interfere one with the other. One objection may be that in an object we can have multiple functions, but the same is true for the closures. For example, with values we can return multiple functions that uses the same shared variable. In this case, we have another counter, which returns two functions, one to increase and the other to decrease. In this case, we can assign using the multiple value bind, or in a setf using the symbol values. The result are two function pointer. When I call the inc, it will increase, while when I call dec, it will decrease. Exactly as we expected. We have an object with two methods. The problem is that if we have really a lot of functions, it is so inconvenient to have the multiple value bind. Another solution is to return a list of functions or a vector of function or a hash map with all the functions and so on. For example, here we have basically a class for a person. The constructor are the parameter passed to the function makePerson. Inside, using a let, we create the closure, and then we return a list of functions. The first one is the getter for the name. The second is the getter for the age, and then we have a function for the birthday that increases the age and print happy birthday. The main issue is that to use those functions, we should use, for example, the first element of this list or the second element of this list and so on. This is the reason why it's really convenient to make some wrapper that just do a funcall of the right element of the list. For example, the getter of the name just does a funcall of the first element of the list person. Here we can see an example of the usage. We create a new person using makePerson, then we print the name, the age, we call the celebrate person birthday, and then we can see the age has been updated. And this is exactly the result we expected. One may think about using the macros instead of function for the wrappers. The main advantage is that we would avoid a function call, because every time we want to call a method using this way, we have exactly two function calls, because we first call getPersonName, which calls first of person. While if we use a macro, it gets replaced during compilation, and so in the end, the final program will just call first of person. We have just shown the main reason why one would use macros instead, but it's a really small performance improvement. If it's not strictly needed, I would always use functions instead. For example, because otherwise we cannot use IOrder function. Here we have a list of persons, and our goal is to get the age of all the persons. This can be done really easy using mapCar, which is a map that applies the function getPersonAge to each element of the list. We can see that the age has exactly the value we expected. Now let's try to declare everything using macros instead. I declare the class and then the macros. The previous example works the same way. But if I call the IOrder function, we get an error. This is because getPersonAge is a macro and not a function. Closures are a really simple concept, but which is everywhere when programming. For a beginner, it's useful to explore closures because they really teach you how to use Common Lisp. And for example, the fact that you have to use funcall when calling a function defined inside a variable. Let me know in the comments if you liked the video, leave a like and subscribe. Functional languages use recursion instead of iteration. Tail recursion is the way to write efficient recursive function. Can we take advantage of it in Common Lisp? Let's start by discussing what is tail recursion. A function is recursive if in its body it calls itself. A classical example is the factorial, which can easily be expressed using recursion. The factorial of 0 is itself, while the factorial of another number is n times the factorial of n minus 1. The advantage of writing recursive functions is that they are often more expressive than the equivalent iterative one. Like in the case of factorial, it can follow exactly the definition. But recursive functions have a big problem. Every time there is a call to a function, some space has to be allocated on the stack, and it cannot be freed until the function has finished. We can see this using trace. Factorial of 10 needs some space, and then inside it calls factorial of 9. The argument 10 cannot be freed when calling factorial of 9, because it will need the value to compute the final result. In this case, the space needed to end the algorithm is proportional to the input. In functional languages, recursion is used instead of iteration, because iteration needs mutation, while recursion can be done using only constants in the lexical scope. That is, local variable can be considered constant, as it happens for the n in the factorial function. We never change the value of n. If it is so important, there must be a way to make our algorithm more efficient. When the recursive call is in tail position, which means that is the last thing in the function, the algorithm can be run in constant space. This is known as tail recursion. The compiler basically rewrites the function using an iterative approach. The previous version of factorial wasn't tail recursive, because the last operation is the product. Nevertheless, the same function can be rewritten in this way. If we look at the return value of trace, it looks like nothing has changed. But if we look at the return value of the function, it is always the same. The problem is that it is not enough to write a function in tail position. The compiler has to optimize it. When we talk about Common Lisp, first of all, we have to look at the standard. And sadly, the standard doesn't require an implementation to optimize tail recursion. Nevertheless, most implementations do. For example, ABCL, which is based on the JVM, cannot implement it. The same thing happens in Clojure. SBCL usually optimizes it. To verify it, we have just to disassemble the two functions. Let's start with factorial. The code is quite difficult to read, but we can see a comment when the call to factorial happens. And we can see that it is using call. Call is the assembly instruction used to call functions. Let's do the same thing with factorial tail. Again, the code is quite long, and we can see that there is a comment when the actual call happens. But this time, instead of call, he is using jump, which means that this is just a loop. It has been transformed in an iterative algorithm. The common suggestion is to not rely on implementation-specific features, and so one should not rely on tail recursion. Every algorithm that can be written using recursion can be rewritten using loops. In the reimplementation of the factorial, we have changed the input. It takes 2 numbers instead of 1. Nevertheless, we can easily change it back using local functions. Labels let us define a function which is local. In this case, we have called it iter, and we can see that inside iter, the implementation is the same as factorial tail. Iter is defined only in the scope of labels. Thus, we will call factorial, which will call iter with the right parameters. The result is that from the outside, factorial looks the same as the first implementation. An alternative approach is, instead of using labels, to use an optional parameter. This way, the user of the function has to provide only n, and accumulator takes the default value, while in the recursive call, we pass the right value to the accumulator. For those that are used to a functional style, they can use tail recursion with known implementation that usually optimize it, like SBCL. Nevertheless, the suggested way is to do without tail recursion and use iteration construct directly. Let me know in the comment if you like the video, leave a like and subscribe. In this piece of JavaScript code, we declare a variable x, then the function foo increases it and prints the value on the screen. Finally, the function main declares a variable x, which is never used. Every time we call foo, the global variable x is incremented and printed. As we would expect, the return value is 43, and every time we call main, the value is increased. This piece of Common Lisp code looks rather similar. We use defvar to declare the global variable, and setf and let to change it. But when we run it, we can see that the result is 144. In JavaScript, all the variables are lexical, which means that their definition is valid only inside a specific block of textual code. For example, the first x is declared global, and so its value can be used everywhere. The second x is declared inside the main, and so its value can only be used at those 2 lines. The same is true if we introduce a new variable with let or with function parameters in Common Lisp. With this code, we would have obtained the desired behavior, because now x is lexical scoped, and so the x we are referring inside foo is exactly the one we declared externally. We can see this is the same behavior as the JavaScript code. On the other hand, variables introduced with defvar or defparameter are special. The name of the symbol refers to the same variable across function calls. When we use let with a variable that was previously defined with defvar of the parameter, we change the value of the previously defined variable. In this case, we have a variable x, which is dynamically scoped, so the let does not introduce a new variable. It changes the value of the global x. This can be seen as an alternative way of passing values to a function. This can be useful. For example, if we have a function that takes input from standard input, like in this example, in which bar sets the variable str to a line read from the standard input, and then returns a string, which is the concatenation of what is read with another string. Now we want to test it. We can use the fact that standard input and standard output are dynamically scoped variable. If I run bar, it waits for input, and then it ends. But I can run with the input from string, which rebinds the standard input to hello. Now, when I run bar, readline will read hello, without asking for interactive input. When one starts writing Common Lisp code, the use of dynamic scope is usually unintentional, which leads to strange bugs. To prevent this kind of situation, the suggestion is to introduce variable with defvar and defparameter using the ERMAF convention, which is prefixing and postfixing the name with an asterisk, as it happens in the case of standard input. Defvar and defparameter have a slightly different behavior. When we use defvar, the value is assigned only if the variable was previously unbound, while with defparameter we can assign the value at every call. We can see this with an example. I set the variable foo to 42, and then I redefine it to 43. We can see that its value is still 42. Now I set the parameter bar to 42, and then set it again to 43. We can see that in the end, its value is 43. This may seem a small difference, but it's strictly connected to the fact that Lisp provides an interactive environment. Assume that we have a file test.lisp that defines a variable, and then it has some function that uses it. Inside the REPL, we load the file, and we can see that it was loaded. Then I start working with this environment, and for example, I change the value of test. Then I change the definition of print test, and now I want to reload the file, but I don't want to lose the changes that I did to the variable test. In this case, I can reload the file safely, and we can see that the value of test is still 2, because during reloading, when interpreter encountered the var, it basically ignored the definition and kept the old value of test. To reload the definition, one has to make the symbol unbound, and then next time I load the file, I can see that test was reloaded. Global variables should be used as little as possible, so at the beginning one should not really deal too much with defvar and defparameter. But there are cases in which one has to, and moreover one may encounter them inside others' code, so it's important to know how to deal with them. For today this is all. Let me know in the comment if you like the video, leave a like and subscribe. Common Lisp has many high-order functions like map, filter, reduce, but they usually work on sequences. What if you want to express a general computation? This is when the series package becomes useful. The series package offers basically some generators. So, when you generate a sequence, it doesn't actually take any space, and when you do some computation on it, it gets executed as efficiently as possible. Let's start by loading the series package and all of its symbols. We start with a simple task, summing the first n natural numbers. We can start with scan range and provide a big number. This is just a pretty print. It hasn't actually loaded all of the numbers from 0 to 1000. To get the sum, we just run collect sum. We can verify what series is actually doing using macroexpand. We can see that it is initializing a variable sum to 0 and the first number. Then number is increased by 1, sum is increased by number, and if we are over 1000, the loops end. This is the same code that would have been executed if we wrote the whole loop by ourselves. Instead of the sum, we can make the product. This is, we basically want to compute the factorial of a number. We start always with scan range, but this time we have to pay attention to exclude the number 0. And then, to multiply, we use the generic collect function, to which we have to pass the type of object we are working with, in this case integer, the first value, which is 1, the operator, which is the product, and then the range itself. One may think that this code is less readable than the previous one. So we define an auxiliary function, collect star, that basically does the product. This is not actually a function because the series package overrides also the CL symbol in order to optimize this kind of auxiliary functions. Then the factorial function is just collect start of scan range from 1 up to n. From the expansion we can see that the result is actually again very similar to what we would have got if we wrote a loop. Series are lazy. We get the value only when we need it. For example, scan range represents the whole set of natural numbers. People familiar with lazy languages like Haskell may see this idea familiar. But the list of natural numbers is a boring series. What about the list of Fibonacci numbers? To get it, we can use the generic scanfn. In this example, scanfn will generate two series, both of integer numbers. The first number of those two series are 0 and 1. The next number of the first sequence is got by the second, while the next number of the second series is the sum of the number of the two series. Then we assign it to a variable f. In particular, the second series will be thrown away, and f is actually the first series generated by scanfn. We can see that the values of this series are actually the Fibonacci numbers. Then, for example, we want to write a function that computes the sum of the first n Fibonacci numbers. Using what we have just learned, it is quite simple. We start from f, we get the first n element using subseries, and then we collect sum. We can see that a warning is shown because it could not really optimize the resulting series. Let's try to sum the first 1000 Fibonacci numbers. The same problem could have been solved also using this function, in which we have two variables, predecessor and successor, to compute all the Fibonacci numbers, sum that will contain the final value of the sum. We use dotimes to repeat the loop for n times. The loop will return the variable sum, and we use a parallel setf to update to the next iteration. Let's try to do the same computation. We can see that the time is absolutely comparable. It's the same order of magnitude. But if we look at the function, the one using series is much more readable. The one with loops contains a lot of logic mixed together, from how to compute the Fibonacci numbers to how to compute a sum and initialize the variable to 0. The standard way to learn about the series package is the appendix of the Common LISP language 2nd edition. As usual, one has to pay attention on what to optimize. The first goal is always to write the code as clear as possible. When there is a bottleneck, one has to run some performance test, understand what is the problem, and re-optimize what is needed. We have already seen in a previous video that even though Common Lisp is a dynamic language, an implementation like SBCL has a lot of type inference, which allows us to find error at compile time and provide us information on how to improve performances. But what if we want more? What if we want a complete type system like one from Haskell? Common Lisp doesn't provide it, but it has a strong macro system that lets the user do deep changes to the language. Coalton is a statically typed functional programming language embedded in Common Lisp. We create a new package in which we load a couple of libraries we need. In particular, there are Coalton and Coalton Prelude. We also notice that inside the use we don't load the CL symbols. We also load some reader macros provided by Coalton. First of all, I have to load Coalton. All the Coalton declaration will have to be put inside a Coalton top level. Let's start with something simple. We want to declare a function isEven. isEven takes an integer and returns a boolean. In particular, it will return true if the integer is even. We can see that inside the Coalton top level we have put a declaration of type isEven takes an integer and returns a boolean. And then we added a definition. isEven takes a number n and returns true if the remainder divided by 2 is equal to 0. Instead of Coalton top level, at the moment we use Codegen. Behind the scene, all the Coalton code is compiled to Common Lisp. I'm currently in the CL user package while I have to move in the Coalton test that we have created previously. Now the generation was successful and we can see that there is a definition of a function isEven that takes a number using the standard Common LISP defun. On the other end, if I try to divide by a string, we can see that an exception is thrown. It's important to emphasize that this is a compile time error. We haven't executed the definition by itself. We've just tried to compile it, but the compilation was not successful. Now we can actually execute the code using top level. Coalton top level. Coalton is strictly embedded inside Common LISP, and we have seen that a function in Coalton is basically compiled to a function in Common LISP. That's why it's possible to call Common LISP from Coalton and vice versa. In particular, calling Common LISP inside Coalton it's always possible. We just have to pay attention that we have to set the type for all the objects of Common LISP. For example, here there is a definition of a function myConcat that concatenates two strings. In the declaration we can see that it takes two strings and returns a string. Then we go to the actual definition. Our goal is to use the concatenate function. We have to express the namespace CL because we haven't used it inside the package definition. But to be able to use this function, we first have to declare the type of string 1 and string 2. And we do this using the Lisp operator. Calling a Coalton function from Common Lisp may be a little bit more challenging. A function like isEven or myConcat that doesn't contain generic types can be called directly. We have already seen during code generation that the function isEven basically creates a defun of isEven that takes a number. The result is that I can call isEven with any number and it is executed directly. As usual, there is the Common Lisp namespace in front of all the standard objects. But we could also have defined the isEven function this way, using the more generic integral class. If we call CodeGen this time, we can see that isEven doesn't only take one parameter, but it also takes a second one. The idea is that if you want to export a Coalton function to Common Lisp, you shouldn't use a polymorphic type. Or, if you use polymorphic types, you should also provide a definition that doesn't use them. Coalton provides algebraic data types. Let's see how to create a binary tree in Common Lisp using them. We define type binary tree, in which each node can contain an object of another type. This is why we say binary tree indexed by type A. The element of a binary tree can be either a leaf that doesn't contain any value, or a node that contains a value and two child binary trees. Then, using the binary tree type, we want to declare a function binary tree height that returns the height of the binary tree. The type of btheight takes as input a binary tree and returns an integer. The binary tree can be indexed by any type. Inside the definition, we do a match on the type of the binary tree. If it is a leaf, we return directly 1, while if it is a node with two child binary trees, we compute the height of both binary trees and return 1 plus the maximum between h1 and h2. The compilation is successful, and then we can call this function in a Coalton environment. In particular, the binary tree height of a leaf is 1, while the binary tree height of a node that just contains two leaves is 2. The main feature of Coalton is the strict relation with Common Lisp. In particular, given the modularity provided by namespaces in Common Lisp, one can choose which part of the software to implement using which language. As usual, Common Lisp provides complete freedom to the programmer. One wants probably to use standard Common Lisp for most of the software, given all the type inference that it already provides. But if there is some namespace that is particularly important or the core of our function we want to be more safe, we can choose to use Coalton for it. Let me know in the comment if you liked the video, leave a like and subscribe. The loop macro is as much effective as non-Lispy. You don't need it, the do macro is enough for any kind of loop, but loop could really improve readability. Today we explore how to write simple loops with the loop macro. Let's start with a simple loop that sums the first n numbers. For example, we want to sum the numbers from 0 to 10. We can make a loop using the below keyword. This will generate all the numbers from 0 to 9. And we want to sum them. We can see the result in the bottom of the screen. We can see what happened when we wrote the loop macro using macro expand. Behind the scene, the macro has created a local variable that starts from 0 and then starts a tag body. Tag body allows us to do some really low level loops. In particular, there is some label, and somewhere in the code we can write go and jump to that particular label. The resulting code is really how we would have written this loop in a low level language using gotos. Lisp is a dynamic language, but if we provide some type information, the compiler can really improve performances. For example, if we know that I will only be an integer, we can declare it as integer. The result is the same, but if we look at the code generated, we can see that I was declared as integer. Below allows us to make a loop from 0 to a specific number. A more generic range of number would be loop for I from 4 to 10 by 2. And we always want to sum I. So in this loop, I will start from 4 and will end in 10, jumping from two numbers to two numbers. So it will go through all the even numbers. Now you start to understand why loop is really non-Lispy. We have really complex expression without any parentheses. Those two expressions evaluate to the same value, but to understand the second one, you need a little bit more experience with the do. Loop is really well integrated to Lisp basic data types. For example, it's really simple to generate some lists. Let's write a loop that goes from 0 to 10 by 2, and we want to generate a list with all the numbers. We can use the collect keyword, and we can see in the bottom that the result is the list that we would have expected. This kind of loop is useful when writing macros. The values that we collect could be some expression that maybe will end up in a program. We have seen how to sum and how to collect. But with loop, we can write any kind of loops. Now the goal is to write a custom expression. For example, we may want to print at screen the values. We start with the same loop, but this time we use the do keyword and we'll make it print. Let's open the console that will contain the standard output, and we can see that this time the result of loop is nil, because we don't have something that computes a value and returns it. But on the screen, all the values appeared. Loop is convenient to generate list, but it's also convenient to get list as input using the in keyword. We will get all the values inside the list, and we want always to print it. The result is the same as we would have expected. In the loop, we can concatenate multiple times 4. So we can have v inside the list and I in a range of values. And as usual, we want to print the values. These may behave slightly different as you would expect at the first glance. We can see that the two lists of values, the list and the range, are run in parallel, and the loop ends when the shortest list ends. Basically, this is a zip in functional programming. If we want to actually nest loop and get the Cartesian product, we have to actually nest loops. So we have an external loop, and then we write another one. In the internal loop, we do the same format. We can see that this time the result is a Cartesian product. Let's try to collect the result of two nested loops. And for example, we just make a dotted pair. We can see that the result is basically a matrix in which a list contains as element another list with all the pairs. If we want to flatten the list in the external loop, instead of collect, we can use enconsing. And we can see that this time there is just one list that contains all the dotted pairs. Now, if we come back to the for run in parallel, the one that did the zip, we have seen that the loop ended when the shortest one was finished. This is an interesting property because, for example, we could write something like we have a range that starts from 42 but doesn't have an end. And then we run in parallel another range that iterates over a list. And for example, we collect the cons. We can see in the bottom that the loop ended even though the first range was in the end infinite because we didn't specify an end. Nevertheless, the end was specified by the second for, which was a loop across a list of 5 elements. Until now, we have seen how to sum, how to collect, and how to run custom expressions. Those keywords can be combined together. For example, we can have the same loop that collects the dotted pairs and, at the same time, prints the value of I. As expected, the return value of the loop was the list with the dotted pairs, but at the same time, we had an output on the console. A last interesting example of loop is how to do the destructuring. In the for, we can replace a single variable with a list of variables if we have a list of elements of the same kind. In this case, we have a list of whose element are a list with 2 elements, and we want to convert it in a list of dotted pairs. Now it's your turn to decide whether the loop macro is worth the effort to actually master it, or if it doesn't really fit your idea of Lisp. For sure, it's an interesting macro that really shows the strength of the language we are currently working with. Let me know in the comments if you liked the video, leave a like and subscribe. Most functions on Lisp follow the decoder. They end when they find a nil and raise an error if what they find is not a cons. But what would happen if each coder points to an element of the list? So if there is not a last element. We can see an example of when this could happen. We can see that the coder of each cons here is a valid element of the list. In this case, many algorithms would never end. So there are times in which it's important to assure that we are not in this case. For this, we have to use a cycle detection algorithm. One has to pay attention when working with cyclic list. In general, also a print could end up generating an infinite loop. Let's start to see how we could create a cyclic list. For example, we could take a non-cyclic list and change the last coder and make it point to an element of the list. We can see that here we take a position and we set the last coder as the nth coder inside this list. Then we define a simple list of 6 elements. In the bottom we can see that this is a usual list, and then we make it cyclic. Now if we try to show it, we can see that Slide detected that there was a cycle and so it stopped to show new elements. In this case we could also take a subsequence and show that from a certain point on the element starts repeating. There are various cycle detection algorithms. The easiest one is probably using hash maps. So we could store inside an hash table each cons of a list. And either we find a repeated element or we stop finding cons. The advantage of this algorithm is that it's simple to generalize also with graphs. So if we also want to look for cycles inside the car, for the moment we just follow the coder. The main disadvantage of this algorithm is that the space required is proportional to the size of the list. because we have to store inside the hash table each cons inside our list. We can see an example of implementation. We keep an hash table of the nodes that we have seen, and then in this case we use tail recursion. So we iterate over the list using tail recursion, and for each element, if we find a nil or an element that is not a cons, so we are not working with a proper list, we haven't found a loop, and so we return nil directly. In the second case, if we have already met this node, then we can return true because we have found a cycle. In the final branch, we set this node as seen, and then we go on with the coder. We can see that it works with our cyclic list, while it returns nil with a proper list or a non-proper list. When we put a point, it means that the next element will be treated as the coder. So in this case, the last element is not a coder that points to nil, but it's directly a number. The second algorithms try to improve the fact that we needed a lot of space in the previous one. So in this case, we have two references in the list, and at each iteration, we move one reference of one step, that is using the coder, and the other of two steps, that is, we get the coder of the coder. In this algorithm, we will often use that the coder of nil is nil. So we have two cases. If the list doesn't have a cycle, then the two references will never meet. That is because one is faster than the other. One moves of two steps at a time, while the other of just one. The second case, on the other hand, if we have a cycle, they will eventually meet. This is a little bit more complicated to see, but if there is a cycle, eventually both references will be inside this cycle, because they keep moving. So we can assign a number to each element inside the cycle. In the previous example, for example, we can see that we have a cycle of length 4, B, C, D, E, and we can start enumerating starting from everywhere. For example, C is number 0, and so they will be 0, 1, 2, and 3. We call A and B the point in which the two references will find at the beginning of the algorithm, when they will be inside the cycle. And what we can say is that after X step, A plus X will be equals to B plus 2X, always if we look modulo the length. And so this congruence has a solution A minus B. And with this we have shown that it exists a step X for which both will have the same value. We can also see an example of implementation. Again, we are using tail recursion, and again we have to look at three different cases. The first one is the case in which fast has reached the end, that is, it has either found nil or an element that is not a cons. We are in the case in which the list doesn't have a loop. The second is the case in which slow and fast have met each other. So in this case we have found a loop. In the final step we keep recurring with the coder. Slow moves just with the coder, while fast use the coder of the coder. Again, we can see that this gives the expected result when evaluated on L. If we want to write a literal cyclic list, Lisp provides a convenient way to do so, using a reader macro. The sharp 1 equal, instead of 1 we could put any number, will be replaced with sharp 1 sharp. Again, the important thing is that 1 is the same. We can see that we have put a point in front of the reference because sharp 1 sharp is a coder. We can try to see the value using sly, and as we would expect, it keeps repeating 1, 2, 3. If we try to print the L, we risk to block the REPL. To prevent this, we set the dynamic variable print cycle to true. Now, if we try to print it, we can see that the REPL has recognized the loop. It's important to see that behind the scene, those sharp are not represented in memory. We can also try to print L. I'm outside of the let, and so print cycle is nil. Let's block the REPL using Ctrl+C, Ctrl+B, and then I print inside the let. As expected, there are A and B, that are the first element of the list, whose coder is the actual cycle, which include C, D, E, and F. For today this is all. Let me know in the comments if you like the video, leave a like and subscribe.